Let's get to the next example for divide and conquer algorithm, and it is quick sort algorithm. In this algorithm, we perform sorting by choosing a key element that is called a pivot, and we partition the unsorted array around this pivot such that all the elements which are smaller than the pivot gets in the left and elements which are greater than the pivot gets in the right side of the pivot element. And if it is equal to the pivot, we can move it either side, left or right. And then we continue to choose pivot and perform partitioning until all elements get sorted. For example, see this is an unsorted array. You choose a pivot element, which can be any of the element, any one element present in this array. It can be first element, it can be last element, or it can be a middle element. You can choose any element. So let's choose 10 as the pivot. Now you perform partitioning around this pivot number, or you can say you rearrange the elements present in this array such that you have one partition having all the elements smaller than this pivot and a right partition having all the elements which are greater than this pivot. So according to this arrangement, 10 gets the third index. And now we say that this index is the appropriate place for this element. But as you can see, still left partition and right partition are not sorted. So again, we apply this whole thing to these generated partitions. We choose a pivot. For the left partition, the pivot is, let's say, 8, and for the right partition, let's choose 90. And then again rearrange the elements by comparing them to the pivot. But still we're not done yet. We have unsorted partitions, right? So we again do this, and this continues till every element gets placed in array in sorted manner. So this was the whole idea of the solution. Now let's think of the approach to achieve the solution. First, how we actually gonna divide problem into subproblems. This is much different than how we do in merge sort. In merge sort, the divide and conquer both steps are very straightforward. But in quick sort, we need to divide problem bit smartly, as the core logic of entire quick sort resides in this step. So pay attention, this is the most complicated part of the algorithm, so the algorithm will make more sense if you understand this logic. So let's see how technically we do this. So here let's pick 10 as pivot. We're gonna take two pointers, left pointer and right pointer. Left is at the leftmost element and right is at the rightmost element, right? Now we will compare left pointer element with the pivot independently. If it is less than or equal to the pivot, then the current element is already placed at the right cell. And we don't do anything and we move on by incrementing the left pointer. And then we go to the right pointer and we compare the element present at this place with the pivot. If it is greater than the pivot, then we are good. The element is at its right place. And then this right pointer moves towards the left. So you're getting it? Left pointer goes towards right and the right pointer goes towards left. But for this example, see the value we're having at the right pointer. It's 0. So if we compare it with the pivot, which is 10, we find that this value 0 is smaller than the pivot. So now the right is stuck here. The right pointer is stuck here. We cannot make a move with it, but we can go back to the left pointer and check out the value present at that pointer. So see, the value is 1 and it is smaller than the value 10. So we can make a move. We can increment the left. Now it is at 67 and the right is still stuck at 0. So again check for the element present at the left. This time the value present at the left pointer is greater than the pivot. 67 is greater than pivot. Now both the pointers cannot make further moves. That is, if the left gets higher element than the pivot and the right gets lower than the pivot, we know elements are out of order. So we need to rearrange them. And that we do by swapping them with each other. So let's swap them. Now the elements get the right place with respect to the current pivot element. And now let's resume with what we were doing. Compare the element with the pivot and make move accordingly. Then there comes a point when the right pointer crosses the left pointer. And this is when we are done with the current pivot. At this point, it's time to perform partitioning. And that we do by replacing the value present at the right pointer with the pivot element. So one iteration is complete. Once this is done, you will see the partitions at either side of this pivot. All the elements at the left to this pivot are smaller than the pivot, and all the elements present at the right to this pivot are greater than this pivot. Now, still this array is not sorted. We have now two more arrays or two arrays from this array. And again, we are going to do the same with these arrays. So we conquer by recursively performing partitioning of the subarrays. Here you can see the first array is from 0 to 2 and the second partition is from 4 to 7. So this is the core partitioning logic. Function will have array, lower bound and upper bound as input parameters, and we will always take first element as the pivot which is present at the lower bound. Left is the first and the right is the last element. Now we will increment the left pointer if left pointer element is smaller or equal to the pivot and when left pointer is less than length minus 1, because it shouldn't go out of the array bound, right? Now talking about the right pointer, we will decrement the right pointer if element at right is greater than the pivot, and we'll also check right is greater than 0 or not, because we don't want to go out of the array bound. And then if both the pointers get stuck, that is, if we're not able to make pointers move to right and left, then we must swap them because the elements are out of order. But again, before swapping them, we must verify that left pointer should be smaller than the right pointer. And this whole process will be repeated until we go through every element. That is, until when left pointer is smaller than the right. But the moment the right pointer crosses the left pointer, we again have to perform swapping because now the process for current pivot is complete. So we swap the elements present at the right with the pivot element as to get the pivot at its correct index. And then we finally return pivot index for the current iteration. Now next step, we conquer by recursively performing partitioning of the subarrays present at either side of index 3. Like here, 10 gets the place at 3. So the partition function returns index 3. So the next recursive call will be for subarray from 0 to 2 and the subarray from 4 to 7. Again, for these, the same process will be continued. Partition returns 2 as 8 get placed at index 2 and 90 gets placed at index 7. Again, for these, the same process will be continued. This continues till we left up with subarrays of single element or no element at all. And finally, each element will get its correct place in the array. So this is how the algorithm works. See the code snippet. This partition function after the execution returns the index of the pivot for that iteration. So we get the index. Now we know either side of the index we have the partitions. So first partition starts from the lower bound to index -1, and the second partition starts from index +1 to the upper bound. So this is how we're recursively calling the quicksort function for the partitioned arrays. We're going to recursively perform this implementation till lower bound is less than upper bound. Now the last step, which is combine. As you've already seen, once the conquer step recursively sorts all the subarrays, all elements get sorted at the end. That's because we're not creating different array for partitions. Rather, we are just rearranging elements in the same array considering the partitioning indexes. So now let's talk about the worst case complexity. A worst case can be you're having the largest number as the pivot. So to find out its correct position, you have to make n iteration to put it at the last index. Right. So you go till the last index and then you put the pivot at its correct index. So you had to make n iterations, right? And then after the rearrangement, you again choose a pivot, and again you have the largest element as the pivot. So you again have to make n-1 iterations to reach to the appropriate index. And this goes on, which makes a total complexity the addition of n plus n-1 plus n-2 all the way to 2, because after that we will only be having single element. So this is an arithmetic progression, and we know that the solution of the series till 1 is n plus 1 divided by 2. But here we are going till 2. Still, it is approximately equal to n plus 1 divided by 2. And analyzing it asymptotically, we will ignore everything other than the term n squared. So the complexity of quicksort algorithm, or the time complexity of quicksort algorithm, is order of n squared. Now let's talk about the space complexity. In quicksort, we're not using extra arrays or space to store elements, but as quicksort involves recursion, we must consider the space that will be taken up by the call stack. So in the worst case, quicksort will be called one time for every element of the list, since the solution could recurse all the way down to single element list. Therefore, we will be having a call stack entry for every function call. This means that at worst there will be n stack entries created at particular instant, and that's why it will be having order of n complexity, linear space complexity.